Hello. In this video, we introduce some properties of functions, like when is a function increasing or decreasing? What are the local minima or maxima? What's the average rate of change? Lots of new stuff, so let's get started. We begin with something that should be intuitive. The idea of when I'm looking at a graph, can I tell when the graph is increasing from left to right, decreasing from left to right, or constant? Well, yeah, that's pretty intuitive, I hope. If we take a look at the picture on the right first to get a sense of what's going on, notice that in this graph, you see that the line is increasing from left to right, starting at the x value of -5 until we get to the x value of -2. So the way we would interpret that is that the function is increasing on that interval, so I would write parentheses -5, comma, -2. That would be one interval where the function is increasing. Now, are there any other places where it's increasing? Well, visually you can see that's happening again, starting at the x value of 1 until we get up here to that x value of 3. So we're also increasing from the interval of 1 to 3. Notice we're only using x values to describe these increasing intervals. Now, what about decreasing? Let me get a new color here so we can see what's going on. Oops, that was not my intention. There's my eraser. So let's take a look at when we might be decreasing for a moment. So in this picture again, where would we be decreasing? That's right. It looks like we're decreasing starting at this location, which is when x is 3, and stopping at this location, which is when x is 5. So the function is decreasing from 3 to 5. So we'd say parentheses 3 until 5. Notice we're always using parentheses for these intervals of change, and we're always describing them with x values rather than y locations. Well, there's one more place that we need to discuss, and that is the areas on the graph where we are seeing a constant progression of values. So no change up or down, no vertical increase or decrease. So where do we see a constant range on our graph here? Do you see it? Yeah, it kind of is spelled out for you. From this value until this value, which is when x is -2 until x is +1. So that would be parentheses -2 until +1. Now in this particular graph, we had stopping points, right? We actually started at the x value -5 and stopped at the x value +5. So if we look and see our intervals here, we should be able to account for every x value between our stopping and starting point, between -5 and +5. Is that true? Well, here we begin with -5 until we get to -2. So there's that first region of the graph. After -2, where do we go from there? Well, from -2, we go to the x value of 1 at a constant rate of change. What about from there? Well, from 1, we would go until 3, increasing. And where do we go from there? You're right, we go from 3 to 5, decreasing. So we've accounted for every single interval along this graph. Okay, so definitionally speaking, how do you know whether or not a function is increasing, decreasing, or constant? Formally, the way we would say it is a function is increasing on an interval, so we say there's an interval. If you pick an x value, let's say x1, and an x value, let's say x2, so for example, in this increasing interval in our picture here, right here, this increasing interval, we could pick any two x values as long as the first x value is less than the second x value. So if we pick this as our first x value and this is our second x value, notice what's happening. Your function's y values, that's f of x1, which would be this y value, and f of x2, that would be this y value here, they have a special relationship, namely that the first y value is less than the second y value. So as long as your first x value is less than your second x value rather, from left to right, then your first y value should be less than your second y value. So that should make sense that you're consistently able to find in this particular interval of the graph, always if you pick an x value to the left of another one, its y value is below the one that is to the right of it. So that's a kind of wordy way and a mathematical way of describing this situation. But as long as you visualize things properly, you don't really have to know the formal definition unless you're moving on in math and you have to know things mathematically speaking. But conceptually, this is very natural for humans, right? We can see when we're rising and when we're falling from left to right. So we can see increase, increase, decrease, constant. That comes intuitively. The definition continues though. If we're talking about when the function was decreasing from left to right, same instructions. If you pick any two x values, let's say this is our x1 here, So at this location, we're like up here somewhere. And then this is our x2, let's say, at this location, so that's like this y value. If you pick those two x values, whenever x1, so this is like your x1, is less than x2, what has to happen? F of x1, so this is your f of x1, this y value, must be greater than f of x2, this y value. And that makes sense if you're truly decreasing, right? Your y values are getting smaller as you move from left to right. All right, and finally, the last part of that definition is also very intuitive, I hope. It's just saying that if you pick any two x values along that interval, no matter which x values you pick, their y values are the same. And that's exactly what you see in that definition. No matter which x values you choose, their y values are the same on that interval. And we see that's what happens here. If I pick this x value and this x value, those y values are identical, aren't they? So that's what we mean by a constant interval. For every single pair of x values, this happens. Okay, so definitionally speaking, we've introduced an interval of change, increase, decrease, or constant. Let's see if you can put that into practice in the next example, using parentheses and x values. Here in this example, we've given you a graph. Now, the difference between this graph and the previous graph is that we don't give you the x values labeled, so you have to do a little bit of thinking here. Let's do some labeling for ourselves. Maybe we call this x value 1, 2, 3, 4, 5, 6, and 7. Maybe -1, -2, -3, -4, -5, -6, -7. So when they don't label things, you're allowed to label them yourself, and I picked an easy scale of 1. Oops, I don't know why I just did that, but you get the idea. They're each worth 1. So what we're going to do now is we're going to say, all right, when is this graph increasing, decreasing, or constant? The second difference between this graph and the last graph is the last graph had starting and stopping points, didn't it? This graph, we notice that there are arrows, which means we are allowed to continue in the same direction that we're going forever. So we have to take that into account if we're going on forever using infinities and negative infinities. So take a moment, maybe use some different colors. I'm going to use this time, let's say blue for increasing. Okay. Can you help me spot the increasing intervals? Go ahead and take your pen and try it yourself and then come back and see how you did. Did you say it was here, increasing, and then again, maybe here, increasing, and again, maybe here? Just visually, right? We can see that, increasing from left to right, it's rising. Now, how do we write those out? Well, again, what were these x values? If we went by ones, this was -1, -2, -3, -4, -5. So it is increasing, we would say, from -5 until this x value. If this is -4, this would have been -3. They're going by ones. When else were we increasing? Well, this would have been -1 until +1. So from -1 until +1, we're increasing. What about intervals which are decreasing? I'll use, let's say, red for decreasing. See if you can do it yourself. Pause the video and then check how you did. Okay, let's see how you did. With your decreasing intervals, would you have said this space until we get to this x value, and then decreasing again from this space until we get to this value? If you did, good job. Those are your two decreasing intervals. But how did you write them? Good. So you noticed you had to stop decreasing at the x value -5. But where did you start the decrease? Yeah, you went up forever. So that would have said the x values are getting further and further to the left, so -infinity. So you're allowed to go on with more and more negative values, and you're still watching this graph fall from left to right. So it's decreasing along that entire interval. Where else did you say the graph was decreasing? Well, yeah, from this x value until not just the x-intercept, but it keeps decreasing beyond the x-intercept until this point. What x value is that? If they're by ones, 1, 2, 3, that would be the x value of 4, wouldn't it? So did you say it's also decreasing from x equals 1 until x equals 4? These are like points in time. Like if you think of this as a roller coaster ride, from this spot in time to this spot in time, it's increasing or decreasing. So we look at that as our labeling, x values. What about constant? Do we see any constant places? For a roller coaster, this would be my favorite part when it's just going straight. Okay, so let's take a look at constant. Did you say between this x value and this x value? So like -3 until -1? Good job. There's a constant space interval, -3 to -1. And then also starting at this x value, going to the right forever. So how did you label that? That would have been at the x value 5. So starting at 5 and going to the right forever, how did you write that? Yep, infinity. Now, before you call it a day with these problems, it's important, after you dissect everything like this, to make sure you've accounted for all of the regions. And that's why I like using different colors, because you can easily see that I've described every region. But what you'd want to do is say, okay, where did we start the graph and where did we stop the graph? Well, we went to the left forever because of the arrow, and we went to the right forever because of the arrow. So we're going to look for negative infinity as our starting point on the left. So here it is, negative infinity to negative 5. Then we're saying, okay, picking up from negative 5, that's where we start increasing until negative 3. And then from negative 3, that's where we start being constant until negative 1. And then from negative 1, we're increasing again until positive 1. And then from 1, we're decreasing again until positive 4. Let's see. Oops, I see a mistake. Where's my missing? Do you guys see what I'm missing? I missed something. What did I miss? Yep, I missed an interval. Which interval did I miss? You might have been yelling at the video for a while here. I missed this interval, which was increasing, didn't I? And this is why this is a really helpful way. I wish I could say I planned that. A helpful way to check that you didn't miss anything. Yeah, it's increasing from 4 to 5. That's what I missed. And so now I can check myself. Yep, in fact, now I'm increasing from 4 to 5, and then from 5 to infinity, I'm constant. Okay, so that's the helpful part. I hope you can see how that you can make a mistake really easily if you're not paying attention. Now, by writing it out like that and checking yourself, did I really discuss every single region? You know you're right. Okay, so we've described it correctly. Okay, a couple things that students usually mess up on besides forgetting a region like I did. First thing they usually mess up on is they want to put brackets instead of parentheses. Brackets usually mean you're including the endpoints, but when you're describing intervals of change, we're not interested in what happens at that precise location, but rather what's happening between those x values. Okay, so we don't actually include those endpoints, so we use parentheses for that reason. Secondly, we're only describing x values. Okay, a lot of students accidentally use the y value, so we're describing x values in time. All right, so we've done some intervals of change problems. The next thing we're going to do is describe what's happening at these points. Let me find another color for you. At these points here, at this peak, at this valley, and at this valley. We have a special name for those points. This will be called a local maximum. This will be called a local minimum, and another local minimum. And what happens, just so you're not confused with the wording in English, when we say maximum or minimum, that's just singular. And then when we say maxima, minima, that's just plural. So if I have multiple values like this, so a minimum here and a minimum here, I would say I have two local minima. So just so you know, we're not trying to confuse you, but that's how English language works. Okay, so let's get to the next slide here and describe this in more detail. Describing plural local maxima and minima. So we have a couple pictures here, and we'll talk about the one on the left in just a moment above me here. But I wanted to begin by describing to you in the box on the right the formal definition of a local maximum or a local minimum. If you take a look at this picture in the box on the right here, we notice that in this graph on the left that we would have a local maximum, and that would be a local maximum because in that particular region from here to here, this open interval here, that is the point which is higher than all the others. It's kind of like if you ever climbed any mountains. There's different elevations, right? But every time you get to a mountain peak, if it's higher than everything below it in its immediate vicinity, that would be called a local peak, right? A local peak. But there might be peaks that are higher than it. So we could have a global maximum that's the highest peak of them all. But in regard to everything right around it, it's still the highest value. So this would be called a local or relative maximum in this case, maximum. So I would say in this situation that my maximum is the elevation. It is the y value. So if this was like, let's say 7, I would say that 7 would be my local max, right? But if I were to ask you, where does that occur? Where is the maximum occurring? You would say it occurs at x equals c. Maybe c is 2 feet or 2 seconds, whatever it is. When does that occur? Now, this will become really important when we start talking about things like projectile motion, when we launch a rocket into the air and we want to know when it's at its highest elevation. So they might ask you when it happens. They'd be looking for c here. When does that happen? Maybe they'll ask you what is the highest elevation. That would be looking for f of c, the y value, right? So understanding what they're asking is important. Notice that the definition of the minimum works exactly the same way. To be a local minimum, that just is saying that in a certain region, you're the lowest y value. You're lower than everybody around you. Now notice that's different than the graph that we saw previously when we had a constant region of the graph, because in a constant region of the graph, every y value is tied, isn't it? So we wouldn't say that that constant space is a minimum or a maximum. Only if there's actually a peak or a valley would we call it a local max or a local min, because it has to be superior, the lower or the highest value in that region, the lowest or the highest value in that region. So here again, we would say that the minimum here, the local minimum, is the y value. Where does it occur? It occurs at the x value. So it is the y value. It always is your y value, but it occurs at an x value. So with that in mind, can you look at the graph above me and tell me where are the local maxes and local mins? Local maxima, local minima. Do we have any? Feel free to pause the video and complete the blanks there. So as far as local minimum go, do you see a local minimum? Yeah, you might say it's this guy, right? That is definitely the valley, okay? So if I asked you what is the local minimum, what did you tell me? What is the local minimum? Did you give me the x value or the y value? Hopefully you gave me the y value, right? The local minimum would be -16, okay? So that is the lowest elevation, if you will, the lowest y value. Now when does it occur? When does it occur? It occurs when x is 2, so at x equals 2. So understanding how to answer these questions is a secondary thing. First thing is understanding visually where they are, right? Where are my local maxes and my local mins? And then understanding how to write them out. See if you can answer the other question about the local maximum and where it occurs. Okay, did you say, well, I see it visually, it's got to be that peak, right? But how did you describe it? Yep, the local maximum is the elevation, the y value of 16, and it occurs where? At the x value of -2. So in your homework and on your test, you'll need to be able to write down the local maxima, the local minimum as the y values, and then where they occur as those x values. Okay, so that takes some getting used to for sure. Let's see if this is making any sense and another example for you to try. Example 2 says, please find any local maxima and local minima for the functions graph below, and then tell me at which value or values do they occur. So again, take a look at the graph carefully here. They have actually labeled some of the spaces on the graph so we can tell what the scale is, what each tick mark is worth. So let's see if we can write those out for ourselves here. If this one is 5 and there's 1, 2, 3, 4, 5 spaces, they must be each worth 1, right? So 1, 2, 3, 4, etc. 5, 6, 7, 8, 9. And you can see 10 next to it. Similarly, on the left, we have -1, -2, -3, -4. There's -5 already. -6, -7, -8, and -9. I know it's kind of boring to write it out, but it's usually going to save you some time later and some thinking. Okay, so now that we have the graph, I could definitely ask you questions about the previous material we talked about, right? When is this graph constant? Well, we can kind of see 2 places where it's constant. When is this graph increasing? You can see a couple places where that's happening. When is this graph decreasing? You can see a couple places again where that's happening. But that's not the question this time. This time they're asking you for what are the local maxima and what are the local minima. Okay, so see if you can pause the video and try it yourself. Do you see the local maxima? Well, visually, hopefully you're saying, yeah, it's happening at this peak, right? That would be where our local maxima is, right? Do you see any other local maxima, any other peaks? Yep, that would be right here, another local maxima. Because around that point, it's higher than all the other points, right? So that's what we consider a local maxima. Okay, so as far as describing the local maxima, how did you do that? Well, you would first look for the elevation, right? What is the elevation, the y value, at this location? It looks like it's at 8. So we would say one of the local maxima is when we have the y value 8. What's another local maxima? That's right, it's at this elevation of 4. So we would say 8 and 4. Now, if I were to ask you what is the global maxima, right, that would be just 8, right, the highest peak. But when I ask you for local maxima, I mean relative to everybody around him, do you see any peaks, right? And we did find them at 8. They are 8 and they are 4. But where do they occur? Those are the x values, right? So 8 is found at the x value, -4. And then we have 4, and that's found at the x value of 2. So they are 8 and 4, those are my local maxima, but they occur at the x values, -4 and 2 respectively. Can you find the local minima? Did you do that? Let's see. For your local minima, you might have been tempted to say this point here. Anyone tempted? It's very tempting, right? But why is that not a local minima? why is it not a local minimum, singular, sorry. Why is it not a local minimum? That's right, because right around it, you can find someone who's tied with him, right? Namely, all of these points, they share the same y value, don't they? So to be a local max or min, you have to beat, if you will, to be either the lower or the higher value than anyone around you. So this y value, this elevation, would not in fact be a local minimum. Do you see any local minimum then that do qualify? Yeah, how about down here, this location, right? That would look like a local minimum, wouldn't it? Notice again here at this value, that almost looks like one, but then it's not because it's constant, so we can eliminate that as a local minimum. So there's only one local minimum, it seems. And how would you describe that, or how did you describe that on your own? Good, it is the y value, the elevation, which is 0. So we're saying that is our local minimum. Now notice you might have thought, hey, wait a second, professor, didn't you just tell me that I couldn't use this point? And I said, yeah, that's true. And that has the same elevation of 0. That's also true. So we're not calling that particular value when we have x equaling 5. We're not saying that is where we have a local minimum. But we are saying that a local minimum has an elevation in this graph of 0. And it occurs specifically, oops, that was not what I wanted to do. Let me grab a pen instead. It occurs specifically at this location when x is what value? That's right, only when x is 0. If I was claiming it's also the local minimum over here when x is 5, I would have had to write that out. But then it wouldn't make any sense because it would be 5, 5.1, 5.2, and every single value right next to it. So that wouldn't make a lot of sense. So there can be multiple local maxima and local minima, but you have to be specific to tell your reader exactly the x values at which they occur. Okay, this will definitely take some getting used to, just getting used to the way we say things and what we mean by things. So practice, practice, practice. Well, next we're going to transition to another example of this. Let's take a look, clear my page. You're going to see in this example, again, maximas and minimas, intervals of increase and decrease, but this time we're going to take a different focus as we look at properties for these two functions. The focus that we're going to take is symmetry and a special name for that symmetry for a certain function. So we've talked already about symmetry. You can go look at a previous video. We talked about y-axis symmetry, right, where you have a reflection over the y-axis. We've talked about x-axis symmetry, but that's really not a function because it fails the vertical line test. And we also talked about origin symmetry from quadrant 1 into quadrant 3 or quadrant 2 into quadrant 4. And that was another type of symmetry for functions. But today we're going to introduce a way of determining that kind of symmetry formally, but also giving a special name to functions with either y-axis or origin symmetry. So I want to begin with the idea of what does it mean to be an even function. Now this will be incredibly helpful for those of you who choose to take a class called trigonometry or calculus. That is going to come up again and again. So what do we mean by even functions? To be an even function simply means that you have y-axis symmetry. That's all it means. Now, practically speaking, if you're given the graph, that's pretty obvious, right? So looking at the graph here on the top here, we see a parabola, and that parabola has a vertex, its lowest point, that is on the y-axis. So it's very nice and symmetrical along the y-axis, isn't it? Notice again, another way of describing that y-axis symmetry is it doesn't matter if you take a positive x value or its opposite x value. The y values are the same. In other words, here's our formal definition. For an even function, for a function which has y-axis symmetry, anytime you plug in the opposite x value, so f of negative x, you get the exact same y value output as you got for plugging in the original x value and getting f of x. So for example, if x was 2 here and we got a y value of, let's say, 4, and then I plugged in negative 2 and I also got a y value of 4, if that's happening for every single x, where you can take its opposite and plug it in and you get the same output, that must be producing a mirror image about the y-axis. And we call that an even function. Now, if you're wondering why we picked the name even, it turns out that if we're describing polynomials like the one I just described, like y equals x squared, for example, if that was the situation, this is actually x squared plus 1, but bear with me. It turns out that for polynomials, if you have an even function, all of your exponents of your polynomial will be even numbers, like x squared. That's the second power. And the reason for that is, if you think about it, every time you put a negative or a positive number in for x, and you square it or raise it to the 4th or 6th or 8th power, any even power, it turns it positive, right? So it doesn't matter if you put in a positive or a negative value. That's why those are called even functions. So that's a little trick. Now with odd functions, It's not odd because they're strange. It's odd, again, for the same reason. If you had a polynomial, every time you have a polynomial where every exponent is an odd number, like 1, 3, 5, 7, 9, etc., if you take a negative and you raise it to that power, won't you get a negative result? So you get the opposite of the y value you started with, which is what's happening in this graph here. Here we're saying if you had an x value, let's say of 2, and that gave you an output, let's say, of 8, but then you put in -2, and that gave you an output of, let's say, -8, that's not an even function anymore because we no longer have y-axis symmetry. Instead, we have a mirror image from quadrant 1 here into quadrant 3. So that's where we have what we called origin symmetry, right? Origin symmetry. And if it's origin symmetry, that really just means that when you plug in the opposite x value than the one that we started with, you will get the opposite output. So instead of +8, now you're at -8 when you use -2 instead of +2 for x. Okay, so how do we determine then if I have an even or an odd function, but I'm not necessarily given the picture? Well, I can give you an example here on the left of the function f of x is equal to x plus the absolute value of x. So let's take a look at this example here. So in this example above, if I wanted to check for even or odd function, I would simply replace every x with -x and see what happens. So if I replace every x with -x, that's what we did in both cases. We said, what happens if you replace x with -x? In the first case, this x becomes just -x. Now notice what that means. If you add a 2 there, now it's a -2. So I'm going to put a little double line underneath it to indicate that I have changed from my original, right? The original was x, and now it's the opposite of x. So that's definitely not the same thing I started with. Let's go to the second term, plus the absolute value of our new input, which is -x. But let's think about what this would produce. If you had x being, let's say, 2, and you took its absolute value, you'd still get 2. It would be the same thing. But what if x was -2? Well, if you took the absolute value of -2, wouldn't you still get 2? In other words, the absolute value of an x is the same as the absolute value of a -x because you always get a positive output. So what I could write is I have -x plus the absolute value of x because these two mean the same thing, don't they? These are synonymous. So we end up getting the opposite of our first value, but the exact same for our second value. This is what we call a mixture, right? It's not exactly the opposite, and it's not exactly the original. So if we have a mixture, we would say, if you remember from the past, this has no y-axis symmetry, and it has no origin symmetry. So it's neither even nor odd. So we would say neither. Neither even nor odd. Okay, that was kind of a boring one, but I wanted to show you a complicated one like that. It's not super hard, but where you have a mixture of things happening. So it's not quite as obvious. So again, as I noted earlier, if you're talking about an even function, what type of symmetry do you have? That's right, y-axis symmetry. And if you're talking an odd function, what type of symmetry should your graph have? That's right, origin symmetry. Okay, with that in mind, you're going to have an example now where you get to put this into practice with the graphs and with the equations. So if you need to pause this and go back and watch it again, feel free to do that before you engage with the next example on your own. So in this example, it's simply saying, could you determine if the functions below are even, odd, or neither? Now, most of the time, they will be neither, but when they are even or odd, we'll have special properties, and that's why we want to make note of when they are. So let's take a look at the functions, for example, that are given to you. The first function we have here is a situation where we have f of x equals 3x to the third power plus 5. Now, it is a polynomial, so we mentioned that if a polynomial has all odd powers or all even powers, then we're done. We know exactly what's going on here. But in this case, it's not quite as obvious for students because the number 5 is a constant. So what is the exponent that's implied there? Is it 1? Is it something else? Well, it's not 1, because if it was 1, there would be an x to the 1 there, just an x, and there isn't. In other words, there's really an implied x to the 0 there, isn't there? Because x to the 0 is 1? Yeah, it's kind of tricky. And is 0 an even number or an odd number? How do you know if it's even or odd? Is it divisible by 2, right? And if it's divisible by 2, it's even. So taking a look here, 0 is divisible by 2, because 0 divided by 2 is still 0, okay? That means that in this case, we have a mixture again. So if we had a mixture of even and odds, then we know this is neither, isn't it? Neither even nor odd. Now that's the shortcut by simply looking at the powers because this was a polynomial. But if you wanted to go through the process, you could have done it that way as well by simply saying, I'm going to plug in -x. And if you plugged in negative x, you would have received 3 parentheses negative x to the third power. But with 5, there's no place to plug in negative x, so I just write 5. And then watch what happens. In the first case, a negative x to the third power becomes negative, doesn't it? So that means a negative is multiplied by the number 3, so you really get negative 3x cubed. So that's the opposite than what we started with. But when we get over to 5, we notice that 5 is unchanged. It's exactly the same as we started with. So that's, again, a mixture, and a mixture means neither even nor odd. See if you can try that process with D on your own, since it's also an equation. Can you plug in negative x and see if you get the exact same thing as you started with, the exact opposite, or a mixture of the two? So take a minute, pause the video, try it yourself. We're trying D right now. Okay, so let's see how you did. In D, you would have said, I'm going to take f of negative x and see what happens, right? So in the numerator, the old input x is replaced with the new input negative x. In the denominator, the old input of x squared plus 1 is replaced with negative x, getting squared in parentheses, plus 1. So what happened to your numerator? Is it exactly the same as you started with, or did we switch to the opposite? Well, it was x originally, and now it's a negative x. So this is definitely the opposite of what we've started with. So far we have an opposite, okay? What about the denominator, however? Now in that denominator, if you take a negative x and you square it, what happened? A negative times a negative is a positive, so this turns out to just be positive x squared, and then plus 1 is still plus 1. So the denominator remained unchanged. Now here's where things get a little interesting, because 9 out of 10 students would probably say, hey, that's a mixture, so neither one. But be careful when it's a fraction, right? When it's a fraction, if you have a negative on top, can't you really say that that negative sign could be written in front? So in reality, if the top changed but the bottom didn't, in a fraction, that is the opposite. This turns out to be the same as negative, the opposite of x over x squared plus 1. Now isn't that the opposite of what we started with? It's saying take the opposite of x over x squared plus 1? It is. So you might be really confused now. Okay, professor, so when would it be a mixture? Or when would it be neither? What if in the denominator one of them changed but one of them didn't, right? So for example, if the x was raised to an odd power and it became negative but the 1 stayed positive, that would have been a mixture. But when the entire numerator changes and the denominator stayed the same, that made the fraction a negative, didn't it? And that made the whole thing the opposite. Now if they had both become opposites, a negative over a negative is a positive, and that would have made it stay the same. So with fractions, you got to be very careful to understand what's going on with those signs. Okay, take a moment now and pause the video if you haven't already tried B and C, and see if just by looking at the graphs you can tell me if we have y-axis symmetry, origin symmetry, or neither one, because by knowing symmetry, you know if they're even or odd. How did you do? Well, in B here, we notice that if you take an x value of 1, that has an output, a y value of negative 2. And if you take the opposite x value of negative 1, that has an output of the same thing, y equals negative 2. And that seems to be happening consistently, right? At the x value 2, we have the output of positive 2. But at the x value negative 2, we still have the same output of positive 2. So when we notice that changing the x value keeps the outputs the same, that's really saying f of negative x is the same as f of positive x. What did that mean again? That means we have y-axis symmetry, don't we? And you could see that from the graph, right? It's a mirror image about the y-axis. And if we have y-axis symmetry, what kind of function was that? That's right, even. If you can't remember if it's even or odd, remember that y equals x squared has y-axis symmetry, and its power 2 is even. So that's a nice way to remember that. What about C? What happened in C? Well, if you notice again, at the x value of negative 2, you had the output of negative 2. But when you change the x value sign to positive 2, you now have the opposite y value. So isn't that saying that f of negative x produces the opposite negative f of x? So what did that mean? That meant we had origin symmetry. And if you have origin symmetry, what kind of function do you have? Yep, you have an odd function. Again, another way to remember which one's odd or even, remember the snake y equals x cubed, right? That has origin symmetry, and its power is odd for that polynomial. All right, so now we've talked a lot today. We've talked about maxes and mins, we've talked about intervals of change, and now we've even talked about when a function is even, odd, or neither. The last thing I want to do in this video is describe to you something called the average rate of change. So let's take a look at one more topic today. The good news is, if you're already tired, there's nothing new in this definition. It's just another name for the same thing. So when we describe the average rate of change on a function, we're saying if you were to pick two locations on a graph, can you see how fast or how slow that particular part of the graph is either increasing or decreasing? In other words, what's the average rate of change? How fast is it going? If you think about it like a roller coaster, there's different parts of the roller coaster where you're going faster or slower. And so we're saying from this spot to this spot, how fast on average are we going? That's basically the idea. So when we say average rate of change, we're really describing the slope between 2 points because that's what slope tells you, okay? So if you remember the slope formula, then you are good to go. It might look a little different, but it's the same thing. That slope formula was if you had 2 points, x1, y1, and another point, x2, y2, then the slope was the change in your y values, your elevation change, over the change in your x values, your horizontal change. So y2 minus y1 over x2 minus x1. So what we notice here is if we had a curve, that red curve, that represents our function, part of it anyway, and we're saying from this location P until this location Q, on average, how fast are we going? What's the average rate of change? So to do that, we can simply find the slope between those two locations. So to find the elevation change, you simply subtract your y values. And to find the horizontal change, you simply subtract your x values. So let's take a look at how we can do that, but with function notation instead of y, f of x, right? So taking a look here at our function, we're told that we're considering our function to be f of x equals x squared. Now you can actually click on that Desmos graph link and it'll pull up the actual parabola here. So just a little sketch here, we remember that that is something like this, right? It's a parabola with the vertex at the origin. So nice y-axis symmetry, nice even function. So we're asking you, what is the average rate of change between the x value of -2? So here when they give you these x values, it's kind of like those intervals of change. Those are x values. -2 and -1. So maybe over here is -2 and maybe over here is -1. So like between here and here, how fast are we changing? Well, we can see that we're going down, right? So it's going to be a negative rate of change because we're going down from left to right. We're decreasing. So it'll be a negative slope. So how did we find the slope between those 2 points? The average rate of change is just your slope. Well, we had to find, for m, our slope, we had to find our y2 minus our y1, so that's our change in elevation, over our x2 minus x1, the change in the horizontal distance that's gone by, or time that's gone by. So the x values are already given. Those are the obvious ones, right? Our second x value, we said the first x value was -2, and the second x value was -1. So we can subtract those, right, carefully. That's just going to be a -1, parentheses, minus a -2. Now, graphically, you can see how far apart they are, right? They're 1 apart, but your sign might be a little different. So here we have -1, double negative means add, so -1 plus 2. What is -1 plus 2? Just +1. Yeah, we knew that those were 1 apart. That's easy enough to figure out. But what about the y values? Now that is where some students get a little confused. You could go to the graph and you could try to figure it all out graphically, but technically the y values can be found. If you have a function, the beauty of a function is that the y values are easily described by simply looking at the output when you plug in the input, right? So for example, if I want to find y2, the second y value, I would simply input the second x value, wouldn't I? So the second x value was a -1. So I would say f of -1. And then to find my first y value, I would simply input my first x value, wouldn't I? So that would be f of -2. My first x value was a -2. So if I put those into my function as my inputs, wouldn't I get my outputs, my y values? So yeah, we can do that now. To find our y2 value, so let me just make that clear for you. This is your y2 and this is your y1. To find your second y value, put in your second x value into the function. So our second x value was -1. Let's put that in. If you put in -1 and you squared it, what number would you get? That's right, just +1. And then we're supposed to subtract our first y value. Well, our first y value was when we put in our first x value. So our first x value was a negative 2 into the function. But the function just says take your input and square it. So take negative 2 and square it. That's what we're doing here. We're finding these values. What is negative 2 to the second power? Positive 4. So I now have 1 minus 4. In other words, if I rewrite this, I'll move up here for a moment, my average rate of change appears to be negative 3 over 1. Now, you know that's just negative 3, right? So we could just write negative 3. Maybe this is in meters per second. Maybe this is miles per hour. We're saying every time your graph goes down 3 units, that's gone a horizontal space of 1. Okay, so we're saying go down 3 and go right 1, or go up 3 and go left 1. That's what we mean by negative 3. Okay, so maybe negative 3 miles per hour, negative 3 meters per second, whatever your units are. Okay, so again, the tricky part for students here is using the function notation, right? What do we mean by y2 and y1? Well, we mean the y values for those inputs, right? y2 is the y value for x2 as your input. y1 is the y value when x1 is your input. In other words, instead of y2 minus y1, you could write f of x2 minus f of x1. And that's how most textbooks write this. F of x2 minus f of x1 means the same thing. But since I didn't want to make you learn another formula, I didn't have it in the actual cleaned up notes, okay? So that's up to you. If you want to memorize a brand new formula, feel free. But if you understand conceptually how to find y values by plugging in the inputs, you're fine. So the last example is you putting this into action. So as usual, feel free to rewatch this part before you head into your last example on your own. Let's clear this up and get to our last example. Example 4, it says find the average rate of change for the function here between 1 and 3. So take a look at this situation. We have f of x equals a negative sign and then x to the third power plus 1. Okay, so that negative sign is in front, meaning you do it after you raise x to the third power. So take a moment and see if you remember how to find the average rate of change as we did in the last example, and then see how you did. Okay, so what did average rate of change really mean? That's right, just your slope. So your slope was your y2 minus your y1 over your x2 minus your x1. Okay, so how did that look here? Here they're talking about what x values? Yep, 1 and 3. So here this is like x1 is the number 1 and x2 is the number 3. So another way of writing this is what is the function's y value when we replace the input with the second x value, so f of x2, and then what is the function's y value when I replace the x value input with x1, so that was f of x1, over the change in my x values. So you didn't have to write it that way, but for some students that's helpful. Subtracting the x values is always the easiest part because they gave them to you right away. So your x values were 3 and 1. That was your second and your first, so 3 minus 1. Now, if you chose to switch the order, just make sure you're consistent. If you call the x value here 1 and 2, then make sure your y values are lined up the same way. Your signs will be opposite, but in the end it works out the same because it's a fraction. So we have 3 minus 1. In other words, 2 is our denominator. Okay? So we're going to have a certain elevation change every 2 units that go by. All right, so as far as our y values, how did you find f of x2 here? F of x2. Well, f of x2 was really just plugging in x2 into the function and finding the y value, the output. So plugging in 3 into the function. So f of 3. And then f of x1 was really plugging in x1 into the function. So x1 was the number 1 this time. So minus f of 1. And take a moment. You can go on the side if you need to. Find your f of 3. Find your f of 1 if you haven't already done so. That'll make it a little bit easier to write your answer down. So f of 3 meant plugging in 3. So if you did that correctly, you'd have the opposite of 3 to the third power and then add 1. F of 1 meant take the opposite of 1 to the third power and then add 1. Notice I put those parentheses there because you have to follow the order of operations, the exponent, before you take the opposite of it, the multiply or divide. So here what do we get? Well, if you take 3 to the third power, 3 times 3 times 3, it's not 9, it's 27, isn't it? So you're taking the opposite of 27, which is negative 27, and adding 1 to it. So did you get negative 26? If so, well done. So negative 26 is your second y value. Then we're supposed to subtract our first y value, f of 1 in this case, or f of x1. Well, that means take the opposite of 1 to the third power. Well, 1 to the third power is just 1, right? And the opposite of 1 is a negative 1. So I have a negative 1 and a positive 1. Combined, that's 0, isn't it? So minus 0. So our first y value was a 0. Our second y value was a negative 26. So it does appear we're falling, aren't we? So we should have a negative rate of change. And that's what's going to happen. It turns out that if you take negative 26 and subtract 0, you still have negative 26. Divided by a positive 2, that results in a negative rate of change. On average, your rate of change, if you reduce it, was negative 13, wasn't it? 13 over 1 if you want to write it out slowly, but it's really just negative 13. Maybe that's meters per second, maybe that's inches per hour. We don't know what that is, but what the units are, I should say. But we know what's happening. Every time I go down 26, I go over 2. But another way of saying that is every time I go down 13, I went over 1 unit. So that would be our average rate of change. Now you might be thinking, is there a way to know your instantaneous rate of change, Professor? So instead of on average, how fast or slow are you going, but at this particular point in time, how fast or slow are you going? Yes, and that is where calculus will come in, and we'll use the difference quotient and a little bit of thinking to find the exact speed at a certain point in time, not just an average speed. All right, that is a lot for this video, so I hope you take the time to practice because math is definitely not a spectator sport, and I'll see you here next time.